Hello everybody, it is an honor for us to introduce our scientific paper at this international conference in the field of thermal engineering. The name of the article is Numerical Research of the Phase Change in Fixed Honeycomb Regenerator for Humid Air. The authors' names are Angel Penev and Lubomir Tsokov, and we are from Bulgaria, Technical University of Sofia Department of Thermal and Refrigeration Engineering. Let's begin with an introduction. Fixed honeycomb regenerators are used in decentralized ventilation system for heat recovery of the exhaust air from the room and provide economy of energy and quality of indoor air. Regenerative heat exchangers in ventilation systems operate under variable climate conditions, variable temperature, humidity, and pressure difference in the building. Unfortunately, this leads to unbalanced, unsymmetrical, and unfavorable operating regimes of the regenerator, and also including the phase change process in the volume of airflow and on the wall surface of the matrix channel. For this purpose, an accurate and flexible mathematical model is needed to study the evaporation and condensation phase change process into the counterflow matrix operating with humid air. In this paper, we present a numerical CFD model that contains the heat and mass transfer process of condensation of water vapor of humid air onto the wall surface of the matrix channel. The fog formation in the mixture flow is not included, but the existence of supersaturated vapor into the airflow is presented through the parameters values relative humidity. And also the phase change process from the water liquid to the ice is not included in the model. The result shows the influence of the condensation evaporation process of the regenerator's thermal efficiency. The next slide is the numerical mathematical model. The geometry and the dimensions of the regenerator and the matrix channel are shown on the screen. The computational grid is made with connection between two spatial domains, fluid domain and solid domain. The numerical method for solving the system of differential equation is computational fluid dynamics based on the finite volume method, and we have chosen the phase change model Eulerian Wolffium coupled with spatial mixture transport model integrated into the software ANSYS Fluent. The system of differential equation of the CFD model are the continuity equation for spatial mixture transport, the mass diffusion equation in the laminar flow for spatial mixture transport, Navier-Stokes equation, the energy equation of the enthalpy of the mixture, the energy equation of the heat conductivity in the regenerator, and the Eulerian-Wolffium system for mass, energy, and phase change equation for spatial mixture. The initial and boundary conditions of the numerical mathematical model are presented on the screen, and the heat and mass transfer process into the matrix channel are shown too. The regenerator channel shows section x equal to 0 to x equal to L for the inlet and outlet parameters of the model during the heating period of condensation and cooling period of evaporation. Simulation starts from the state of heat and mass equilibrium, and the initial parameters of the Wolffium are specified 0. The direction of airflow through the matrix is reversed after each half period and for each flow switching. The temperature field in the matrix and the fluid at the end of the heating or cooling period are saved in the CFD code and set as the initial condition for the next half period. The boundary conditions have periodic flow conditions with constant inlet temperature, inlet velocity, and inlet mass fraction of water vapor during the heating and cooling period. The outlet boundaries are specified as zero pressure. The next slide shows the numerical results of mass transfer process. The results from the mass fraction of water vapor for the two half periods in the quasi-steady state regime are shown in the graph. During the heating period of the outlet mass fraction of water vapor at x equal to L started to increase, but remained lower than the constant inlet mass fraction at x equal to 0. This decrease of the concentration of the mass fraction was due to the condensation of the water vapor into the channel. During the cooling period, the outlet mass fraction of water vapor at x equal to 0 briefly increased, but due to the intensive evaporation of the condensate, and after that sharply began to decrease until reach the constant inlet mass fraction at x equal to L, as a result from the full evaporation of the condense. The indicator for the phase change phenomena is the film thickness of the condense. The increase of the film thickness during the heating period proves the intensity of condensation of the decrease is a sign of the completing evaporation of the water liquid during the cooling period. The values of the relative humidity greater than 1 specify the process of condensation near to the wall and into the volume of airflow during the heating period. After the heating period, the process of evaporation during the cooling period is started. Because of the fact that the source of water fog formation is missing in the model, it can be assumed that the values of the relative humidity greater than 1 are defined as an indicator of the existing phase change and fog into the volume airflow. Numerical results of the heat transfer are shown on the screen. The main parameter influencing the intensity of heat exchanged into the channel is the heat transfer coefficient. The constant values of the heat transfer coefficient without phase change process is an indicator on the possibility that such as parameters could be used in the analytical method for evaluating the regenerator's thermal efficiency. The average value for the heating and cooling period of the different Nusselt numbers for laminar heat transfer without phase change are shown on the same graph. The graphs show that in the case of an evaporation and condensation process, the value of the heat transfer coefficient are changed. For the regenerator's channel over the time, it is used as a parameter with a constant value is not acceptable for analytical solution, and in this complicated case, other criteria must be found for the definition of the heat transfer coefficient with phase change. The change of the airflow temperature over time in the outlet channel operating with dry and humid air are shown on the graph. These temperatures were calculated for the average value and were used to evaluate its thermal efficiency by the following expression on the screen. The thermal efficiency of the dry air is equal to 67.8% and the thermal efficiency with phase change is equal to 58.2%. And the conclusion of this article are written on the slide. The developed simulation model of an air regenerator with a phase change reflects the influence of all essential parameters on the heat and mass transfer process in the matrix and allows estimation of local and average values of a large set physical quantities related to the regenerator operation. Following additional verification and validation procedures, the model could be used to perform numerical experiments to optimize the regenerator. The results can be used to obtain appropriate analytical model equations suitable for engineering compliant methods and computer program in order to evaluate the operation of the regenerator for periods of time under operating conditions close to the real nature. We would like to thank you for watching the presentation, and we hope that you understand the essence of our article. Wish you good luck and health and regards from Bulgaria.